Welcome to the live session of this NPTEL live session 10, and we will wait for some few more minutes for others to join and then we will start the class. Okay, so if there are any questions in between or you want to discuss anything from the previous class, you are welcome to discuss it all. Please feel free to ask. If you can't ask in the call, then you can also post it here in the chat box. Okay, so I think I should share my screen now so you guys can easily access the screen, and then we will wait for a few minutes, like 1 or 2 minutes, and then we will start. Okay, so okay, let's start. So yeah, session is getting recorded. Okay, so I hope this screen is visible to you all, and let's wait for 1 or 2 minutes for others to join so that everybody can benefit from this live session. So have you guys gone through the previous lectures? I think there was a good vacation of 3 or 4 days. So Saturday was off, and then this Monday is also off. And then in between Sunday was there. So I think you guys must have enjoyed this long weekend. And also you must have seen the lectures which the professor Kalita has actually posted on the NPTEL website. So please go through them. If you have not gone through the lectures, please go through them. That will help you understand the concepts and actually help you in grabbing the concepts. So that is very good. Okay. And if there is anything in between which you can't understand, then please inform me. You can also ask it in the NPTEL discussion forum. Otherwise, you can also ask it here in the live session, because the live session are actually interactive session to help you guys grab the concepts, and if anything you want to ask. Okay. Okay, so let's start the session then. So let me see if the recording is going on. Yeah, it's going on. So that's not an issue. But the main problem is with recording only. And okay, so let me introduce this session. So once again, good evening to you all. Welcome to the live session of NPTEL course. This is live session 10 being conducted on 2nd of October, and this course is being taught by Professor Pankaj Kalita. He is a professor in IIT Guwahati, and I am Rohit. I am a PMRF scholar in IIT Bombay. I am taking this live session. So before going through this session, what I planned, because in last class many of you have raised that this conceptual questions should conceptual part should also be discussed, because you guys were having problem in actually solving the this assignment questions. So basically when you understand the concept, then only you can approach the assignments question properly, because you have to think like what is being asked in the assignments. Okay, so what I have thought, that I will have a quick revision of these topics, and then we'll go through the assignment questions of the previous year. So let's start from this. Okay, so let's have so in this lecture, professor has basically discussed the fundamental of concentrating collectors, and then analysis of parabolic trough collector also be discussed. So concentrating solar power technology. So basically concentrating solar power technology is something which utilize a focus on, because the word concentrating is there. Okay, so you can understand that if word concentrating is there, then it must be concentrating something. So it's not like a flat collector where it collects the sunlight and then absorbs it. Here the main concept is like the beam is concentrated. Okay, so concentrating solar power technology utilizes focused sunlight, and it increases the amount of incident energy on the absorber surface as compared to that of concentrator aperture. So for this, what can be used? So mirrors, lenses, anything that concentrates and convert it to high temperature heat can be used. Okay, so this is actually a concentrated collector. So this is a reflect disk, okay, or disk you can say, and sunlight is coming, and then it actually focuses the sunlight. And here the main concept is that it focuses the, which we have two types of radiation, and diffuse radiation and beam radiation. Only beam radiation or direct radiation can be concentrated, because diffuse radiation will be like this, then it will be diffused in some other way, okay, some other direction. So this is actually can be called a disadvantage here, but yeah, this is the main concept. Here the receiver where you can put the solar cooker, it can be heated, or anything water heating system, and it has got a very high energy and temperature. Okay, so take a look at this slide. This is basically a very important slide, and if you have any questions, please ask. Okay, so uh, you guys could figure out this thing.
Okay, so I'm sure you could understand this concept. This is not a very big and pretty big concept with
To discuss, you just have to understand how the beam are getting focused. Okay, so yeah, these are some of the advantages like higher delivery of temperature, reduced losses due to less material requirement. Storing heat at higher temperature results in reducing the storage cost also, and temperature as high as 35 degrees Celsius has been achieved. So yeah, you will learn about it. Yeah, temperature 3500 degrees Celsius at point concentrated can be achieved, and basically there are heliostates also that also achieve a very high temperature. Okay. So drawback: no use of diffuse resistance as I discussed, and clear sky is preferred in location. Okay. So functioning, so there is a concentrator, then receiver absorbs and converts sunlight into heat, and then heat is actually transported to a steam generator or engine where it is converted to electricity. So CSP technology generate heat from a variety of applications ranging from remote power systems like few kilowatts to up to megawatts also. So I'll not go into much detail of this thermomechanical system because many of you may not have a background in mechanical. So yeah, this is something like it, the heat is can be converted, so whatever happens in power plant like heat is converted to electricity, same thing can be happened here. Okay, so there are various cycles. So there is a Rankine cycle, Stirling cycle, and Brayton cycle. So if anyone wants to know about this cycle, you can ask me. Okay, I can explain it. But for your understanding, a simple understanding, these are various cycles on which the various components of power plant work. So this can be utilized. And limitation, conversion efficiency low, 9 to 18%. And what is the conversion efficiency of a power plant? Steam power plant? So generally it's 30 to 35%. Okay, so it can go as high as 45% also with IGCC plants, combined cycle waste heat recovery. Okay, efficiency decreases as the collection temperature increases. Solar collectors are generally more expensive than engines. And then a part of thermal energy lost during the transportation of working fluid from the collector to heat engine. So this is the main thing. So I want you guys to focus on this diagram. Okay. So there is a high temperature heat receiver. The fluid carries the heat from steam generator. Then from steam generator, steam turbine is rotated, and then this steam turbine is coupled with generator that produces electrical energy. Okay. So there are various flow diagrams. Heat rejected, waste heat also. So this is very important. I want you guys to focus on this. Okay. Okay, let me see if recording is going on. Yeah, everything is going on fine. So there is no issue, there no much issue on that. Okay, so yeah. So yeah, do you have any questions on this, students? No questions? Let me see. Oh, I don't know why it's happening again and again. Network error. Maybe I have some firewall. I'm doing it from the laptop, and then this firewall is getting triggered. So yeah, I'm extremely sorry for this. Let me share the screen again. Okay, so two boys are there. Okay, so if you have any questions regarding the concepts, please put it. And I think you guys have got a good understanding about this. So now let's move to the. So these are some of the concepts like aperture area, absorber area. You can go through the slide to get into it, and acceptance angle. Okay, so basically, I wanted to intercept factor. Okay, so there are two concentration ratio which you need to understand. One is geometric concentration ratio, that is ratio of aperture area to the absorber area. Okay, so don't get confused. This is ratio of aperture area to the absorber area, not otherwise round. Okay, and local concentration ratio is ratio of solar radiation at any point on the absorber surface to the incident radiation at the aperture of the solar concentrator. Okay. So okay, so this is how this has been. So sun is assumed to be a black body. So what is a black body? The black body is something that absorbs all the radiation that is given to it. Okay, it doesn't emit anything, matlab, reflect anything. Okay, that is black body. And radiation from the sun on the aperture receiver is fraction of the radiation emitted by sun, which is intercepted by the aperture. Yeah, that's true. And sigma here is Boltzmann constant. So you have to remember this value. A perfect receiver such as black body radiates energy equal to AR/TR, okay, and a fraction of that reaches the sun. So this is actually how the radiation equations actually go to. This is sun to radiating surface, and this is radiating surface to sun. So when TR and TS are the same, the second law of thermodynamics require that QSR be equal to QR dot S. So A upon AR, R square upon R square, ERS. Okay. So now since maximum value of ERS is unity, yeah, that's okay. Only it can vary between 0 to unity. The maximum concentration ratio for circular concentration is R square upon R square, that is 1 upon sine square theta S. And for linear concentrator, R upon R, 1 upon sine theta S. Okay. So with theta is equal to 0.267 degree, the maximum possible concentration ratio for circular concentrator is 46,000, and for linear concentrator it is only 215. Okay, so you can see the difference here, the kind of values which we are getting here, 46,000 to 215. That's a huge difference, making a huge difference to amount of energy that can be concentrated. So these are various configuration. I think with the figure itself, you can know what type of concentration are there. So C max on point focusing, line focusing 1 upon C. And in the first three types, the maximum concentration ratio is only 4. Okay, only 4 because of flat plate collector. Okay, and actual C value is much lower since greater than. So remember these can be asked in exams also, like why the acceptance angle is usually greater than, why the actual values are much lower. So this is a very beautiful graph which depicts the variation of concentration ratio with the receiver temperature. So with low concentration ratio, the receiver temperature is less. Okay, and with high, as the concentration ratio increases, the receiver temperature also increases. So cylindrical, conical, and paraboloid, like parabolic disc collectors, you can see the high temperature of receiver can be there. Okay, so flat plate collector and concentrating collector. So these are some of the comparisons. So you need to understand very with, with much detail, like what are main difference. Okay, so there are mode of classification of concentrating collectors, like one is based on aperture type, like refracting type utilizing Fresnel lenses, and reflecting type utilizing mirrors. Okay, so it may be parabolic, spherical, or flat. Based on image formation, like non-imaging type or imaging type. Line focusing, point focusing. Okay, based on operating temperature, low, medium, high, and then based on tracking mechanism also. So concentrating solar character. One is parabolic trough, dish Stirling, central tower, and then Fresnel reflector. Okay. So with these are beautiful diagrams. I think if you have in mind these diagrams, you can easily understand what is basically being asked. Okay. So I will leave you guys with this slide for quite some time, so you guys can understand and ask any question which is there in your mind. I really want that you guys should ask questions, because these are very important to get understand these questions. Okay. Okay, so did you guys got this concept? Okay, so did you guys got? So this is a very interesting difference, and then it has been listed in a tabular form. Please go through it because this is a. So it says that it lists the different CSP technologies and possibility of storage integration, and then advantages and disadvantages. Okay. Then if you want to do thermal analysis, so yeah, S is basically solar beam radiation per unit area, and A is effective area of radiator concentrator, and QU is rate of useful heat gain, and QL is rate of heat loss from the reservoir. So this is what it can be explained as, and then rate of heat loss in terms of overall heat loss coefficient can be given as this. So yeah, this is the expanded form. This is how it works. Okay, so UL is basically overall heat loss coefficient, and by combining the above two terms, it is AAS minus UL upon C, that is C is concentrating ratio, and then TPM minus TA. So CSP system efficiency as a function of receiver temperature. So yeah, at the receiver temperature and system efficiency, this shows the function of so it reaches a maximum optimum value at some temperature and then it goes down. Okay. So for this the flat plate cutter C equal to 1, this optimum value, and then this is the basically how much it can go. Okay, and N system efficiency is basically N collector into N Carnot. So these are various utilities that can be done, and this is what the operating temperature can achieve from this solar concentrating solar power. Okay. So this is basically the analysis. This is the tube. So observed tube area is pi d naught into L. Okay. So that is surface area of the tube, and then effective aperture area is W minus d naught into L. Okay. So this is actually the concentration ratio. Please look through it, and I will explain the everything. So before going to the, I think there must be some numerical also. So we will go through it before going to it. So have a look at this. Okay. So these are various equations that has been derived for analyzing a parabolic trough collector. Please look at it, and if you have any queries, please feel free to ask me to it. Okay. And let me see if this is going on. Yeah, the recording is going on as it is. Okay. Okay, guys, did you got it? I think you must have understood the different concept discussed here. Please have a look at these equations. These are very important equations. Okay, and if there are any thing which you want to ask, please ask me. So, guys, are you getting the concept here? See, these three slides are very important if you want to understand the concepts. Okay, so like Nusselt number, like when we were deriving the equations in the previous lectures also. So we had discussed the Nusselt number and how these things actually work. Okay, so these are very important, like Churchill and Bernstein. So yeah, these are various correlations which are used to estimate the value of heat transfer coefficients. Okay, so these can be used. Okay. So yeah, this is the last slide of this lecture for this heat trans parabolic trough collector. So please look at, like we have also discussed the detached Voltaire equation. Okay, please have a look at this. Okay. So now let's move to the next lecture to discuss the this lecture slides 26 to revise the different concepts in lecture 27. So I think you guys must have got a good understanding about this, the various concepts. So if you have any questions, feel free to ask. Okay. Yeah, huh, yeah. So you want to ask about this? Okay. So this Nusselt number, why it is important? You are asking, na? Huh, yeah. This Nusselt number is basically important because we need to know the heat transfer coefficient, and you know Nusselt number is HL upon K. Okay. So that is characteristic length. L is not length; it's characteristic length. Okay. So based on this, we can get the H value, and then we can evaluate the heat transfer and other phenomena. Okay. So that is why we actually study and use these equations. So yeah, these are various. Earlier we studied the parabolic trough. So have a look at this first. Okay.
Okay, so yeah, these are various components. So basically discussing these things are not so necessary because you already know like various components of parabolic trough systems like parabolic reflectors, receiver tube, metal support structure, tracking systems. This is this animation here. So what happens here, the cold water comes and it flow through the receiver absorber, and it gets hot and then leaves from the other side. This is the main thing, okay? And whole thing is, the whole concept is here only. Whatever heat transfer or anything is going on here only. And this is basically this shape which you see. This is trough system, parabolic trough. This basically concentrating the solar rays to this uh, tube, okay? So this looks like this. This is the main image which shows this concept here. Being recorded now. Yeah. Okay, so you got understanding about how this works, this parabolic trough system, and this is basically axis of rotation. So it tracks the sunlight. This is a very important diagram. Have a look at it. How it can be used for power generation. Okay. So what happens? The sun rays are concentrated on this receivers, and then the hot water converts to steam, and then it rotates the turbine and electricity generated. This is as simple as that. So these are arranged in line because one of them cannot be actually used for this electricity generation. So these are actually arranged in line for generating electricity. Okay. So now you must have got a good understanding about how it works. Now we will talk about one of the very important, which has a very high concentrator ratio, parabolic disk system. So it's like a large satellite dish, which you can see it here, and has mirror-like reflectors and absorber at the focal point. So here it is the absorber. Okay, it has a very high concentrating ratio, and it had dual axis tracking. Okay, parabolic trough has only single axis tracking, but it can have dual axis tracking. It can go like vertical also and on horizontal plane also. So this is what is very important. So this you can see array of this arrays of parabolic disk concentrator. So this is the working principle. Okay, have a look at this working principle. So this is basically the solar disk parabolic disk Stirling engine, which you can see here. This is how it works, and then we will moving towards the this uh, so central tower. So these are arrays of mirrors called heliostat that are arranged, and it has dual axis. It focuses the rays of the sun on a concentrating receiver, central receiver that is located on a tower, and it can generate a very high degree of temperature. Okay, very high degree Celsius. So this is analysis of central power receiving system. check if the recording is going on. Yeah, it's going. Okay. So this is the concentration ratio, and basically we have to calculate the size of the image that is being built on the observer. That is can be obtained from this equation, which is given here. You can see the equation of size of the, if the mirrors are flat and if mirrors are suitably dished, like we have this dished parabolic disc reflector, then it can be calculated from this. Okay, and area of the observer can be calculated from this. And Van Til and Hindenburg suggested that observer shape should be a spherical segment of a conical section. Okay, and the concentration ratio can be obtained from these equations. So yeah, now let's move to the this problem. So after moving through this problem, then you guys will have a good idea about. So first read this question, and then I will discuss this question for you guys to understand.
Okay, now let me discuss this concept here. Discuss this question here, which you guys are actually demanding. So let me discuss it. And if you feel that if anything is there to discuss, please feel free to ask me. Okay. So basically, the question is in a central receiver. Let me see the recording is going on. Yeah. So the question here basically says that in a central receiver character, the height of the tower. So tower height is basically 150 meter. Okay, and rim angle is 50 degree. That is this. It is talking about this. Okay, and the diameter of the mirrors are 4.5 meter. Find the size of the image found by the outermost mirror at the receiver's area of observer, concentration ratio. Calculate the above for flat mirrors and then dished mirrors. So we have to assume like psi equal to 0.38 and theta equal to 0.002 radians. Okay. So alpha radian equal to alpha degree, that is 0.53 into pi into 180. Then we can get it into alpha radians. Then using these formulas, we can calculate the this size of the image, area of the observer, and concentration ratio. Now start. Let's start for flat mirrors. So Li equal to for flat mirrors C. Okay. So see here, H upon H. How much was H? 150. Okay. 150 on cos phi r. Theta is plus theta e plus W. So 150, and then we have cos phi. How much it is given? 50. Okay. And then 16 to 32 pi upon 16 to 180 plus 0.002 that we have taken here. Theta e, the value of theta e. Okay. And then we have added 4.5, that is from here, the diameter of mirrors. So with this we calculated for flat mirrors the Li equal to just 7.14. Similarly, putting the values, we get the value of AP equal to 1115.67. And then we use the formula for C, that is psi pi h square tan square phi r upon AP. So you know psi from here, you know phi r, you know h square, that is 150 meter square, then tan phi r, tan square phi r, and then AP which is calculated from here. Okay. And phi r is basically 50 degree. So yeah, this can be calculated. Similarly for dished mirrors, you can calculate it and see the value, the difference value. The size is actually 2.64 here for same configuration, and this area is 15.82 meter square. Okay, so it is asking the area of the observer. So basically this can consider it on a very small this aperture area, but see the concentration ratio value 330 to 2412. So you can see the calculate the concentration ratio value and you can see the difference yourself, how much this mirror concentrate and how much flat mirrors concentrate. This is a typical heliostat system for power generation. This is the central receiver, and here the central receiver is located, and these are the various cells, various discs or flat mirror that concentrates the sun rays to this central receiver,
and there are pipelines which take the steam and then power is generated. Okay, so have a look at this. See the beautiful view of this, how beautifully it is arranged. This is what the science and engineering is. Okay. Okay, so now you could have understand, you could have got it easily, the concept here. You must have got a good understanding of the this molten salt storage system. So basically, this is, as the name suggests, it similarly stores the energy in the form of molten salt. Through this, the Rankine cycle is actually operated and power is generated. So hot salt is pumped into steam generator system that produces superheated steam for conventional and kind turbine generator system. And this is basically a type of heliostat. Okay. So average reflectivity 0.9 reduced to 0.82 due to dirt. So dirt plays a quite important role. And this is what tower receiver is. This is very important when you are discussing about these things now. These play a very important role actually. These tower receivers, these heliostats. See the design, intricate design, and it actually accepts the concentrated rays and molten salt is basically used. So these are basically various types of um, uh, prototypes, or you can say actual plants based on this central tower system. So output is, you can see a quite good amount of output. A big one is solar one, that is 10 megawatt. It's in Bairstow, USA. Heat transport fluid is steam, not molten salt. And 1982, it was constructed in 1982. Okay. And now we are moving to the Fresnel reflectors. So Fresnel reflectors are like mirrors which are arranged and it focuses the light. Yeah, this is the main concept of Fresnel. They're basically based on the mirrors that focuses light on the central tubes. Okay. So this is how it operates. Okay.
So it's already 8:33. So I think these things which you guys have got a good understanding about. And this is a basically overall chart of concentrating solar technology. So we have concentrating solar thermal, we have concentrating solar PV. So this is totally a different concept working on directly converting it to electricity. Here the heat is main product. So this is what the different collection is. And this is symmetric parabolic truck power generation. Okay. So you guys got understanding how it is working? So basically, like this is molten salt, okay, and this is oil circuit. Then this is heat exchanger that exchanges the heat, and then this is steam boiler where this is used to heat the steam. Actually, so this is basically oil circuit. This overall. This is cold and this is hot. And this is how this steam to water to oil heat exchanger. Steam is generated, then power is generated, then it goes to condenser, and then it cools down, then goes back into the circuit. So this is a parabolic truck power plant. This is how it looks like. Okay. So these are the collectors. These must be the oil circuit. These are storage. These must be the heat exchanger. These are condensers and power generator system. So Okay, so these are very beautiful pics, and this table is very much important. Okay, so go through this table very much, and now we are moving to the assignment questions. So let's discuss the assignment questions first. So, because it's already 8:39, and then we will. So I won't focus much on assignment because the questions are very easy, and some theoreticals are there, some numerical questions are there. So I want you that you guys should try to solve those questions, okay? Because all the formulas which is needed is given in the lecture slides. You just have to put it. Like I have solved the numerical, which you in the while I was discussing and showing you the how to approach the numerical and solve it. So you have to do it like that only. You have to identify what are the data given, list it down, and then apply the formulas and get the answer. So the extent up to which the incident beam radiation may deviate from the normal to aperture plane and yet to reach the observer receiver is termed as. So this is basically what we were knowing. This is acceptance angle. Okay. And what is this? Which of the following solar device could generate maximum output temperature? So paraboloid concentrator, cylindrical paraboloid concentrator, central tower receiver, Fresnel reflector. So this is central tower receiver. Why central tower receiver? Because the tower is there and then surrounding large number of arrays of solar concentrators are there. Okay. So this actually helps in generating a, and this is actually a parabolic disc concentrator. I put actual pic here so make you understand how this is work. So this is a microcontroller unit for axis tracking. Then there are sensors also to sense the sunlight reaching. This is parabolic disc concentrator which has mirrors in it, and it focuses the light to air. This is insulated cavity receiver. Okay. The overall performance of solar parabolic trough collector is influenced by. So it also improved by aperture width, trough length also, rim angle also, all of the above. So correct answer is all of the above. The mirror reflectors in parabolic disc concentrating collector are continuously adjusted to their focal point by using. So it's talking about parabolic disc concentrator. Do you know for parabolic disc concentrator, dual axis tracking mechanism. Heat transfer fluid used in solar power system where temperature receiver goes above, goes close to 1000 degrees Celsius is basically molten salt, like we have seen in the lecture slides also. So these have much lower temperature, water only 100 degrees Celsius and to 300 degrees Celsius, so superheated steam. For central parabolic concentrator with an acceptance angle of 60 degrees, the concentration ratio is. So there was a formula given for acceptance angle. So you put it the value in that formula, you will get the concentration ratio is 51.63, and you have to use the center parabolic concentrator, not flat plate. Okay. And there is this numerical in a central receiver. The height of tower, rim angle, and diameter of the mirrors are this. The mirrors used for collector are considered to be flat, like this is flat. Okay. Angle subtended by the sun at Earth is 0.53. If the fraction of ground area covered is 0.42, and angular error is that theta e, which is basically value assumed also. You can assume it also 0.002. Generally, this value is there. The size of image formed by outone. So there was this Li formula, na. You just have to put the values, and it will be 7.6. I think this question was solved also. I think 45. No, it was 50 degree. Okay, 120 degree. The similarly, you can calculate the C concentrator ratio, like we have discussed in the numerical. So correct answer will be B, 342. And then there is this. So I want you guys to solve this question. Okay, solve this question. For collector having aperture area of 360 meters, the concentration ratio of 24. The observer surface achieves a temperature of 480 degrees Celsius. The overall heat loss coefficient. So H value is given, aperture area is given, concentration ratio is given, Absorber and sunbeam radiation is this also given. The rate of heat loss is basically calculated to be 40.77, and the rate of useful heat gain is basically 200.43. Okay, now solve this question. I think this is basically you have to use the concept of center, and there is a parabolic disc collector and basically 200,000 heliostats. So these three questions you have to solve. How much time is there? So yeah, enough time is there to solve. You have 15 minutes, solve it, and then I will show you the answer.
to solve this question? Okay. So, did you got the question? So basically, when we see the question says a central receiver collector system consists of 2000 heliostats, each 5 into 5 meter in size. So this is a central tower, okay, and there are heliostat lines lined surrounding it, okay, and these are 2000 in number. So n equal to 2000, and each heliostat has size of 5 into 5, okay, 5 meter into 5 meter. Height of central tower is 90 meter, okay. Rim angle is also given, that is 70. Theta is E is given 0.004, and heliostats are dish type. Okay, suitably dish. The angle subtended by sun on earth is 0.53. So I think this was a question also. This question was also discussed, na? Like we will solved it in the like. Similarly, the size of image form Li value. So put this thing into this Li value, Li formula, and you will get size of image format 3487. The size of receiver, okay, put the value, you will get it at 33.785. And similarly, the concentration ratio will be 1480. That is good amount of concentration ratio. You can even see the option and you can also guess. Like generally, it's parabolic disk, so concentration ratio will be very high, 1480. Okay. So with this, I am ending this session. It was nice interacting with you guys, and it was yeah, you guys asked a lot of good questions. And actually, when you go through the lecture side, most of the numerical question you will be able to solve. So just go through it, and whatever question is given, just solve it again and again. Okay. So that will make you guys confident about your answers. Okay. So thank you all. See you on next Monday from 7 to 9. Okay. Thank you. I'm ending this session here.